Welcome everyone to our session of the high school research. My name is Mingyu Xu, and I'm associate professor in statistics and data science at the University of Central Florida. Today, we have three talented and passionate young scholars presenting their research work. They all have many accomplishments in various competitions in the world. Our first speaker is Mulan Wu. She is a high school junior at the University of Chicago Laboratory School. Please join me welcoming Mulan.
Okay, I'll share my screen. Right. So my research was on the confidence intervals based on the modified chi-square distribution and its applications in medicine. I am from the University of Chicago Laboratory High School, and this project was done in collaboration with Dr. Dong-Yun Kim at the National Institutes of Health. So here's my table of contents. We'll begin with the motivation behind this method, and then the details for both the standard and the new method, some simulations, and then lastly, illustrations with real data. Motivation. In clinical studies, small sample sizes and proportions are common due to high costs, limited subjects, and/or rare conditions. When the sample size is sufficiently large and the proportion is not too small, we can approximate using a normal distribution to calculate the confidence interval. However, when we have a small proportion, we can't use the normal distribution. So we propose a new method based off of the results of Xu et al. 2019. The standard method for confidence intervals. We're using the Wald method, which is a confidence interval is equal to the mean, p hat in this case, plus minus the z-score times the standard deviation over the sample size. The bounds are calculated by the following inequalities, which is the last set of inequalities that you see on the slide. For the new method, we'll begin with Pearson's chi-square distribution for 2 degrees of freedom, so Q equals 2 in the sum. By Xu et al., we introduce a new correction term. The entire expression is less than or equal to 1.96 squared for the 95% confidence level. So the expression at the bottom, chi-squared minus the sum plus 1, should be less than or equal to 1.96 squared, and we'll be solving that inequality. By solving the previous inequality and setting the right-hand side as 0, we can now solve the following quadratic equation for p. After solving the quadratic equation, we'll get two roots, r1 and r2, where r1 is less than r2. Those roots are the lower and upper bounds of our confidence interval calculated using a new method. So by using this method, instead of using mean plus minus z-score times standard deviation over error, we'll be solving the quadratic equation by plugging in our numbers, and then the roots from the equation will be our confidence interval. So next we have some simulations. A Python program was developed to compare the two methods. We use sample sizes of 30, 50, 100, 200, and 300, along with proportions of 0.01 to 0.09 to generate confidence intervals using both the new method and the standard method. We're using really small proportions because our goal is to find a way to generate confidence intervals for smaller proportions because those are pretty common. We also calculated the empirical coverage probabilities of the true proportion falling within the confidence intervals. This was also repeated for confidence intervals of 90, 95, and 99 to assess the accuracy further. So this is where the confidence level is 0.95. The blue points are the empirical coverage probabilities obtained from the new method, and the orange points are from the standard method. As you can see, when we compare the magnitudes, we see that the orange points are inconsistently close to 95 when the proportion is less than 0.05, while the blue points are closer to 0.95 across all tested proportions. We do see that the orange/brown points are closer to 0.95 when the proportion is greater than 0.05. However, when it's less than 0.05, it's a lot more unpredictable. Similarly, this is a graph where the confidence level equals 0.99. We can see that here the results are even more apparent. So here I have a table of the summary of the results from the simulation. We have highlighted some of the more apparent results. You can see that when the proportion is 0.01, the standard method is not very consistent across the different sample sizes, and in fact, very off when both the sample size and the proportions are small. You can see that in the sample size 30, proportion 0.01, under confidence level equals 95, we get 0.964 from the new method, which is fairly close. Well, for the standard method, we get 0.260, which is extremely far away. However, when the proportion is sufficiently large, we can see that the standard and the new method are not very different, as you can see in the last row, where the sample size is 300 and the proportion is 0.09. Looking at confidence level equals 0.95, we can see that 0.956 from the new method and 0.949 from the standard method are both very close. So the new method with the correction term is good for very small proportions, but if you have a proportion that is greater than 0.05, the standard method is sufficient. This is the data from the HF Action clinical trial that we use in the illustration. It was a multi-center, two-arm, unblinded, randomized controlled trial, and it studied whether or not exercising reduces mortality or hospitalization. The cases in the trial were patients with left ventricular dysfunction and heart failure, and the primary endpoint was time of death or all-cause hospitalization. So we have a few illustrations with this data. First, we'll look at the overall data. The total death proportion is around 17%, and we can see that because the proportion is fairly large, the bounds calculated using both methods are fairly similar. However, people will be interested in analyzing the subgroups of the data. So we chose the subgroup of control versus treatment in females in region 3, which is northeastern USA. We can see that the treatment group death proportion for females is 3%, which is fairly small. So we can use the new method to illustrate the accuracy. We see that in the control group found using a new method, the bounds are from around 6% to 18%. In the treatment group, the bounds are from 0.9% to 8%. We see a little overlap between the lower bounds from 6 to 8%, but overall, the new method is better. So here is my list of references. The first one is Xu et al., where the new method was derived from, and the second one is the study in which I got the data to illustrate with. Thank you for listening. If you have any questions, feel free to contact the email.
Thanks, Mulan, for the excellent work and presentation. For the interest of time, we are going to postpone all the Q&A to the end of the session, and the audience are encouraged to contact the authors and presenters after the session. So our next speaker is Daniel Wu. Daniel is a high school junior from the University of Chicago Laboratory School with a passion of intersect STEM and legal applications. Please join me welcoming Daniel.
Hello. Thank you for the introduction. So this is my presentation on the ethics of artificial intelligence as they pertain to medicine and healthcare law. Again, thank you, Dr. Xu, Dr. Kim, and everyone else involved in organizing this conference. And I'd also like to thank my boss, Dr. Chan, for providing me with the opportunity and resources to research this conflict. So yeah, I am a high school junior at the University of Chicago. Okay, at the University of Chicago lab, sorry. Okay, so the problem that I wanted to address in my research is how can we harness the power of AI in healthcare without harming patients? And moreover, what are the ethical concerns of AI and how should we approach them? And how can we make sure that patients trust AI? And secondly, what legal problems have already arisen and what should we gather from them? And in my research, I wanted to focus on some legal cases, what has already been tried and judged, and how is legislation keeping up with AI, which moves so fast, and how should we move forward in a legislative sense? So first, I want to highlight some uses of healthcare AI. So in detecting cancer, for example, algorithms continue to outperform radiologists in spotting tumors and lesions. And in surgery, AI robots may enhance a surgeon's vision and help create minimally invasive incisions, which is helpful in like heart, head, neck surgeries. And lastly, in diabetic retinopathy, AI automatons can speedily detect diabetic retinopathy and prescribe appropriate treatments. And these treatments are made available to people in underserved communities, which ensures treatment for all patients regardless of socioeconomic status or geographic location. So then in my research, I identified 4 main ethical concerns for healthcare AI. So first, algorithmic biases and prejudices. So when an AI model makes a decision, it's formed by the data that it receives. So the first way that usually a bias manifests is from the data set. So if the data is full of biases, the AI will easily perpetuate these inequalities. But second, also the feature selection plays a big role. So the bias or the prejudice can arise from what the engineer wants the AI to take into account. So for example, if the AI model is analyzing medical data and this data include the patient's race, and if the engineer tells the AI model to pay attention to the race, it may perpetuate a racial bias. So for example, some studies of AI in pulse oximetry and allocating need-based healthcare showed evident discrimination toward African-American patients because of data disparities. Okay, second, explainability. So having an AI model that can explain the decision is very important in healthcare, because if an AI model is going to deliver a prescription and it can't explain its thought process behind the prescription, the patient won't feel very inclined to, adhere to that prescription. So a lot of AI right now is black box, which means that whatever it's doing to make its decision is a mystery. And to combat this, a new field of study called explainable AI is developing AI models that can actually explain their decisions, which is a major development in this field are methods that test and compute the importance of certain input features. And this has already been applied in methods for detecting COVID-19. So third, user privacy. There are usually 2 ways in which user privacy is violated. Either corporations are careless with sharing data and they deliberately violate a contract because the legal repercussions are too low, which is a problem in of itself, or the AI model itself can be coaxed into revealing private information or re-identification. So some solutions that have been explored are homomorphic encryption, which is where the AI model is going to analyze data and do computations on data while it is still encrypted, and differential privacy, which allows a lot of corporations and people work on the development of an AI model without having to actually share or transfer data, which will prevent data breaches. And last, sustainability. So just some statistics. ChatGPT-3 used 700,000 liters of water in its training process, and one single ChatGPT-4 uses around the same amount of energy as it takes to charge a cell phone. And so even though AI has helped sustainability and environmental health, for example, processes in optimizing resource allocation, researchers and developers should be mindful of the environmental impacts of AI and should be focusing on developing environmentally conscious AI models. So moving on to kind of the legislative part that I researched, I identified 2 major case studies that highlight these ethical concerns. The first one is the estate of Jean P. Loken and Dale Henry Tetzlaff versus United Health Group. So this class action lawsuit is accusing the insurance group, United Health Group, of wrongfully denying medical claims resulting from the outputs of this predictive decision-making black box AI model. It's forced thousands of elderly patients to prematurely lose insured access to care and to thereby spend tens of thousands of dollars for care that should be covered under government-funded Medicare plans. So the families of Loken and Tetzlaff both had to pay substantial out-of-pocket costs for the 2 men. They appealed these costs, and then an investigation was carried out, which discovered that the AI model is pinpointing the precise moment when the insurance group can shut off payment for a patient's treatment. And there was also a pronounced discrimination against the elderly patients and disabled patients. And it's also overruling these real human doctors' decisions. Furthermore, this model was reported to have a 90% error rate, and the insurance group was firing and reducing the pay of doctors and nurses who stray too far from the model's estimate. And it just became very clear that the insurance group using this model was this big unethical scheme for money. And millions of Americans were dependent on this insurance group that was using this AI software unethically. So this lawsuit is still ongoing, but it's very likely that the plaintiffs will win. And it emphasizes why explainable and unbiased AI developed by ethical corporations are very important in healthcare. Often, not only is maybe the AI unclear about its decision, but sometimes the corporation won't have your best interest to heart as a patient. And yes, it's very important. So the second case study is Matthew Dinerstein versus Google. So in 2016, the University of Chicago and Google signed this data use agreement, which authorized the University of Chicago to disclose anonymized personal data, which included things like medical procedures and test results, to Google for the development of a medical predictive modeling software. So Dinerstein was a year prior an inpatient at the University of Chicago twice, and his data were included in the data that was transferred. And when he found out about this, he claimed that he had not explicitly consented and that the defendants had violated the hospital patient contract. He also claimed intrusion upon seclusion. And this claim basically meant that because he was using a smartphone during his stay at the university, and this smartphone had geolocation capabilities, and he had downloaded numerous Google apps during his inpatient treatment, this would have granted the company access to his precise location. And then he alleged that Google could have compared his location data with the anonymized data and then ascertained his identity and uncovered his private details. So while these claims sound plausible, Dinerstein wasn't able to actually show any actual substantial injury. And plus, the paperwork that he was provided with, which he signed, outlined ways in which the university might use his data. And so the judge ultimately ruled in favor of Google and the university, saying that while Dinerstein's claim for hospital patient violation stood, nothing else did, and he was unable to prove sufficient injury. So even though Dinerstein didn't win this case, his stories and actions might encourage institutions and hospitals to be more clear to patients about how their data is being used and shared. But that being said, what this case also highlights is that something hypothetical, something that wasn't injurious, won't necessarily qualify as a violation of user privacy. So last, I wanted to talk about current legislation and some steps moving forward. So first, a very like this behemoth legislative work that's been passed very recently is the European Union's AI Act. So passed in the spring of this year, it starts with this risk-based classification of different AI systems. So there's unacceptable risk, high risk, limited risk, and minimal risk. And so the EU says that unacceptable risk AI is straight off the market for us. Most of the act is about these high risk systems, and high risk is basically most of the AI out there, like anything used to collect data or used in very practical fields tend to be high risk. And developers are required to continually document modifications and design the system to ensure that human input can override it, which as we've seen with the Logan case study is very important. So next, there's the White House AI Bill of Rights. So passed in 2022, this addresses kind of this problematic patient care systems, and it's centered around protecting citizens' democratic and civil rights. And there wasn't a lot on how to implement it, but it was used as a set of guidelines for American AI developers. It basically has these principles. It's saying you should be protected from unsafe AI. You should not face discrimination, and you should be able to opt out of using an AI system whenever appropriate. And lastly is the executive order, which was passed a year after the Bill of Rights, and it builds on the Bill of Rights, and it's much more comprehensive. It goes into specificities, and it stresses the importance of labeling AI-generated content, for example. And it also requires the developers of very powerful AI systems to share data with the government. So we hope that in the future, more detailed and dynamic legislation will continue to ensure user safety and work toward harnessing the power of healthcare AI while eliminating injury. So thank you, and if you have any questions, you can direct them to my email here.
Excellent work. Very interesting topic. Thank you, Daniel, for sharing it with us. So if the audience has any question or discussion, please talk to Daniel. So our last speaker is Jiajia Huang. She is from Huron High School in Ann Arbor, Michigan. Please join me welcoming Jiajia.
Okay. Hi, everyone. My name is Jiajia. I'm a junior at Huron High in Ann Arbor. This research was conducted in collaboration with the University of Michigan Department of Statistics with Professor Yang Chen and the various other graduate students that helped move this project. So to start off, what are solar flares? Solar flares are localized bursts of electromagnetic radiation that originate from the sun's atmosphere that are associated with sunspots. They send high-intensity energy, light, and high-speed particles into the atmosphere. They vary in terms of duration and magnitude, so lasting anywhere from a few minutes to several hours. large solar flares are capable of causing radiation storms, radio blackouts, and even damage to our own satellite operations, communication systems, and power grids here on Earth. Thus, predicting solar flares accurately is crucial to mitigating these harmful effects or even stopping the potential damage of solar flares before they are incurred. This is very imperative, especially in the context of a worsening climate crisis. So being able to accurately surmise the parameters behind varying magnitudes of solar flares would vastly contribute to our understanding of solar activity. So to expand more upon my research, the goal of this research is to predict the magnitude of solar flares using machine learning models with a specific focus on the period from 2010 to 2024. I developed 4 different machine learning models using varying techniques to execute predictions. So my data is derived from space weather HMI active region patches, chart parameters, which are measured from solar active regions. They provide critical information about solar magnetic activity just before a flare occurs. I've listed a few, but there are many more. So my data set consists of 7,355 events. For each event, there are 5 continuous time steps with 16 chart parameters per time step. So each event has 80 predictors. This is a very expensive data set that allows my model to capture the complex relationships between chart parameters and flare magnitudes and form much more nuanced and precise correlations between the two. And they represent different aspects of solar activity in the hours leading up to a solar flare. I divided my data set into a training set, validation set, and test set using a subroutine in Python that divided them proportionally to avoid overfitting. The training set was used to essentially, as the name states, train each model into identifying the parameters and how that correlated to the subsequent category. The validation set was used to validate and further fine tune the model, and then the test set was ultimately what I used to test and experiment to see the actual accuracy of each model. For the sake of simplicity at the beginning of my research, I split the 5 different classes of solar flare magnitudes into 2 broad categories: strong flares that would have a significant impact on the outside atmosphere when emitted, and weak flares which were rather inconsequential in their possible ramifications. So to go in more depth onto the various machine learning models I employed in this research, first off, I'd like to talk about the random forest model. In short, random forest creates multiple decision trees, each trained on a random subset of the data. Predictions are made by averaging or voting across these trees, which reduces overfitting and improves robustness. It handles high-dimensional data like our 80 chart predictors and manages class imbalance as well. Second, I use the gradient boosting classifier, and the way that works is it builds decision trees sequentially, where each tree connects errors from the previous ones. It optimizes through gradient descent, focusing on hard to predict examples, and it's very good at capturing complex and nonlinear patterns in the data, which helps with predicting flare magnitude. Third, I use the stochastic gradient descent classifier, which uses linear models and logistic regression to update weights for each data point using stochastic gradient descent, as the name suggests. A very fast and efficient optimization technique that is efficient for large data sets, but I found it to be less effective when analyzing nonlinear patterns, making it more limited for complex solar flare data. So my neural network, which is the last one, is composed of layers of interconnected nodes, neurons. It learns to detect complex patterns by adjusting weights through backpropagation and gradient descent. So it captures nonlinear relationships in the data, making it powerful for this task, although there must be more. I found that I had to put more effort and attention to make sure that the model was tuned in order to avoid overfitting, which it unfortunately was very prone to. So as you can see, each machine learning model has its unique strengths, and by comparing their performances, we can better understand which is most effective at predicting solar flare magnitudes. So to evaluate the accuracy of my models, I used several graphical and visual interpretations, such as confusion matrices and receiver operating characteristics, ROC curves, to evaluate each model's accuracy. These visualizations allowed me to see where each model performed well and where they struggled, particularly in predicting extreme solar flare magnitude. Skill scores were also metrics I used in a quantitative sense to assess how well the models made correct predictions in the total context of how many strong and weak flares that there actually were. So overall, the accuracy of each model was pretty high. However, this will segue into my first major challenge that I encountered during this project, so which was class imbalance. So although the model seemed to perform well on the average, the imbalance, which refers to the fact that there were exponentially more low magnitude flares than high magnitude flares, kind of skewed results. So most predictions were for the more common low magnitude flares, while high magnitude flares, which are rarer but far more important to predict because of their larger ramifications, were often misclassified. So even though the accuracy appeared good overall, this was largely because the models were correctly predicting the majority class, and they struggled with the rare high magnitude flares, meaning that models weren't as reliable in terms of predicting for critical situations where accurate predictions mattered the most. So to counter this, I implemented threshold adjustment. So by shifting the decision threshold between strong and weak flares, I made the model more sensitive to high magnitude flares, which helped improve performance for these rare events. I used synthetic minority oversampling technique, so it artificially creates more examples of high magnitude flares by generating synthetic data points. So by balancing the data set, I aim to give the model a better chance to learn from the underrepresented class. Third of all, class weighting. So I adjusted the importance of each class during training, assigning higher weights to underrepresented high magnitude flares. So this helped ensure that the models didn't ignore these critical cases in favor of the majority low magnitude class. So as you can see here, my ROC curves, they all look pretty great in terms of the area under the curve, which is indicative of the accuracy of each model. However, as we said, this is very misleading as the class imbalance leads to more strong magnitude flares being mispredicted, which obviously will have a serious consequence due to the damaging effect of strong magnitude flares that are not properly being made aware of beforehand. So showing my confusion matrices, you can see that there is a huge like disproportionate ratio in terms of weak flares and strong flares, and then which is particularly shown in the first row. In the second row, you can see that the results look much better in terms of true positives and false negatives being mitigated. So this is before all the 3 adjustments I made that I addressed in the last slide, and then this is after. So as you can see, results improved and hopefully will continue to improve. Overall, the random forest model showed the most consistent performance, balancing accuracy with computational efficiency. So future directions for my data, I hope to improve my models by and its predictive power by incorporating additional solar measurements beyond sharp parameters such as data from other spacecraft or instruments measuring stuff like corona and solar wind, including real-time solar wind and magnetosphere data to track the progression of solar events more effectively would give us a very updated and nuanced view of solar events as they're happening. So this real-time capability would be especially valuable for early warning systems, allowing for timely actions to mitigate the impacts of solar flares. So obviously continuously fine-tuning my models using SMOTE and class weighting. Future work could explore more advanced techniques for handling class imbalance, such as generative adversarial techniques to synthesize realistic high magnitude flare events or cost-sensitive warning to penalize misclassifications of rare events more effectively. To conclude, most space weather forecasting nowadays still relies on statistical or physics-based models, which may not be as updated, nuanced, or accurate as machine learning is. So by updating our models, predictions reflect current solar trends and events. So by incorporating more parameters, enhancing predictive value by having more detailed categories. So instead of broad classifications, we break down each class into specialized subcategories based on whatever you're looking to examine. Models will continuously become more accurate and suited to its place in astronomy and space weather forecasting. So yeah, thank you all so much. And if you have any questions, feel free to contact me by my email down below. Thank you.
Great work. Thank you, Jiajia. It's exciting to see our young generations to presenting their great work. So we are going to leave the time to the next session. And if the audience are interested, please direct your questions to the speakers. Thank you.